So yeah, I should have it graded by next week after Thanksgiving, most likely. Okay, so let's just start it. So before the midterm, we were talking about solutions. We were talking about mixing of things, right? So we were talking about ideal solutions or ideal mixing. And the key idea in ideal solutions or ideal mixing was that if you have Na moles of A at temperature T and P, and it is separated from Nb moles of B at temperature T and P, and you assume everything behaves ideally, then we had the enthalpy of mixing as 0 because they are ideal, so there is no real interaction going on. And the entropy of mixing was not equal to 0. And in fact, we derived an expression for the entropy of mixing. The entropy of mixing turned out to be minus R XA ln XA plus XB ln XB. So this was assuming ideal behavior. And then we started talking about what happens in the next level of complication, which is regular solutions or regular mixing. And I want to write down the final expression here, and then we will work through it as to where it comes from. The idea in regular solution, regular mixing is that the delta mixing of S, the entropy of mixing is kept the same as that in an ideal behavior, in an ideal mixture. Okay, so we don't change that one, that stays the same. Why don't we change that one? Because we are just building a model. We are allowed to do whatever we want to do. These are the terms, these are the how we set up this model. However, now these particles are actually interacting with each other in some complicated manner. There is a potential energy, there is something else going on. So this delta mixing H is no longer equal to 0. And it's already possible to write down the expression if you think about what it will look like. So we are thinking about how two things mix with each other, right? So it's going to depend on the mole fraction of A, and it's going to depend on the mole fraction of B, right? If it had a term that looked like some coefficient, let's call it K multiplied by XA plus L multiplied by XB, that would be very odd. Why is this a very odd expression for the enthalpy of mixing? Because if you set XB is equal to 0, XA is equal to 1, you would still have an enthalpy of mixing. That does not make sense. There is no mixing, right? So this simply does not make sense. So the simplest thing that you can think of for enthalpy of mixing must depend on both XA and XB at the same time. And the simplest function that depends on XA and XB at the same time is XA multiplied by XB, right? So that's the motivation here. So this is in the regular solution model, omega multiplied by XA XB, where omega is the regular solution parameter. So what we will do today is to, and I started talking about how to derive this expression delta mixing H using something known as the quasi-chemical model, and that's what we will work on today. Before we do that, I want to take a moment to really understand what's going on here. And the key thing here, and in fact, the delta mix H part is still kind of trivial. The non-trivial expression is still the expression for entropy, right? So, and we saw last time that this thing is always positive, right? Because XA is always positive. Go ahead.
Is there a motivation why the delta mix H of like it kind of depends on XA and XB in a symmetrical way. Is there a reason?
It's just the simplest model we can think of. So you can build up, there are lots and lots of complicated models here where people add coefficients. Omega 1 multiplied by XA XB, omega 2 multiplied by XA square XB, omega 3 multiplied by XA XB square, and they go on and so forth. This is the simplest thing you can think of. And the reason will come, it will become more clear. Just wait for it. That's the quasi-chemical model will give you more intuition. So just wait for it. Before we go further, I want to take, and this is your pop quiz. It's not really a quiz, it's a simple thing. It's a good point to take a moment and think about it. Just take a sheet and toss it back. If you have some extra, if you have extra, pass in this direction. So the question for you is, we got the entropy of mixing as positive. But what is entropy? That's the question. What is entropy? In 684. So please don't write, and I want your names on it, okay? I want your names on it. Don't write S is equal to K log W. We are not doing stat mesh here. What is entropy in 684? I want you to take a moment and think about, and then we will come back and see why this expression makes sense. Okay, so that's your question. What is entropy? Yeah. I don't know. If you're done, just come and leave it here. Okay, let's wrap this up. Very good. Okay. So the reason I asked you to do this is because we started with what is entropy when we started this semester, but it becomes kind of abstract. Once you finish this semester and someone asks you what is entropy, you will go back to the same old, the number of ways of arranging things, that's equal to K log W, which is useful. We'll do that in the next semester. But there is a reason why we do things the way we do it in this semester, right? To develop an intuition for where it comes from. So there are many, we started by defining entropy as there exists a state function which is maximized at equilibrium, right? And which depends only on NVE, and it had wonderful mathematical properties. So, and I want you to think about, why does our definition of entropy make sense in terms of this? Why is it that you can justify that the entropy of mixing for two ideal gases is positive? Anyone wants to take a shot at this? We just wrote the definition of entropy. So in connection to that, why is this justified?
So
Yeah.
I think of entropy as a measure of disorder, like
No, there is no disorder.
it's the negative gradient of the Gibbs range.
There is,
With
that's
respect
a bit
to
circular.
the information of the
No information. This is exactly why I asked you to do this. The information, disorder. You're reminding me of the time I tried to be a mathematician. You know, this was in India. I was 17 years old, and I went to a graph theory class, and the professor asked me define permutation. But just like you, I raised my hand. I'm like, it's a number of ways of arranging n things in n places. And the professor goes, he was Bengali. Is anyone Bengali here? He goes, keep hot bhukchish, which means what garbage are you trying? He goes, what is things? What is places? And then he goes, a permutation is a bijection from a set onto itself, which actually makes a lot of sense. So you have to be rigorous. We haven't talked about disorder and order. We had talked about information. You saw it later. Go ahead.
Well, I thought about it as how we expressed before, how we're lifting internal constraints.
Internal constraints, exactly. Good. If I had a chocolate, I would have given you one, Nick. So that's what I want you to think about. Entropy is something that NEX, where X could be volume and other parameters, without internal constraints, is always going to be more than NEX with internal constraints. Okay, anytime this ends up corresponding with it. Yeah, go ahead.
What if I try to mix water and oil and I remove them from constraint?
Then you have to think about energy. You have to, everything is consistent. So don't try to trip me here. Everything is consistent, but you're going to derail me instead of tripping me. I promise you I won't get tripped. I will come back, but let's stick with this. Okay. And that's what regular solutions will allow us to do because we have energy. But this is something I want you to remember. Okay. At the end of the semester that, and if you don't remember it, remember Nick's face, looking down upon you and judging you for talking about entropy as disorder and information. Those are all correct. And we will have a load of fun with that in 687. But this semester, the main point is its constraints, right? It's that's where it comes from. So in this light, does it make sense that our entropy of mixing of ideal behavior is 0, right? Because when we had these things partitioned, we had an internal constraints. We are saying A stay here, B stay here, B stay here, and then you mix it, right? So that's where it comes from. Good. Now let's go back to what Omar asked. Why do we have this omega xp? Where is it coming from? And that's what the quasi-chemical model allows us to do. So quasi-chemical model, we started working on it last time. And there are two key assumptions here. The first assumption is that delta mixing edge is actually very close to delta mixing U, okay? Remember what is H? H is equal to U plus PV. So you're saying that pressure volume term is kind of similar. So unless you have a liquid changing to a gas in the middle of all of it, the mixing, and we are not really talking about a phase change during mixing, right? We are kind of assuming it's similar. So unless you have something drastic going on, this is an okay assumption. And for solid state materials, this is a fantastic assumption. For solid state materials, delta H is in fact very close to delta U. As you go to liquid, the assumption becomes weaker. As you go to gases, the assumption becomes more and more weak. But here, this is an okay assumption. This we talked about last time. The next assumption we did not talk about last time, and this is where I want you to think carefully. This is going to be a different order of complexity than this first one. Last time we started talking about number of bonds, right? We said PAA is number of AA bonds. We said PAB is number of AB bonds, and we said PBB is equal to number of BB bonds. So today we are essentially going to do combinatorics and play with this thing, understand where it's coming from. So second assumption says that we always have a random arrangement. So, and I want to classify one thing. If you purely want to do thermodynamics without thinking about atoms, without thinking about arrangements, then this is all we have, omega xa xb, and we stop here. So quasi-chemical model is a bit more fundamental than thermodynamics. It looks at the atomic picture. It does talk about arrangement and concepts like that. So we always have a random arrangement of atoms. What do I mean by that? It means that if I want to think about PAB, the number of AB bonds, and actually it turns out I don't need to care about AA and BB, and you will see why those terms disappear. Okay, so number of AB bonds can then be written as Z, which is the coordination number of any atom, and we assume that the coordination number is same. If we are doing liquid, there will be a distribution across the coordination number, but this is not a terrible assumption. Next semester, when you look at G of R curves and things like that, you will see that there is a peak even for liquids. So we assume one coordination number multiplied by the total number of atoms, okay, in this system, multiplied by mole fraction of A multiplied by the mole fraction of B. And this is where that term XAXP really comes from. If it's a purely random arrangement, then the number of AB atoms, AB bonds is going to be this quantity. I'm not going to delve too much into this. I'm not going to grill you in the exam. This is something for you to meditate over. I mean, I will just be repeating myself that I would draw a few things and try to explain, but if this is not clear, let's have a discussion on Slack about this. So you have, and you can see why it makes sense in the limiting cases, at least, right? If X is equal to 0, you don't have any AB bonds. If XB is equal to 0, you don't have any AB bonds, right? So, and the number of bonds should also be linearly dependent on the coordination number, right? If the coordination number is 24 instead of 12, you expect the number of bonds to double, right? That's the idea here. So it linearly depends on everything. And it should linearly depend on number of atoms also, right? If you double the number of atoms, the number of bonds should go up. It should double. So that's the idea. It's linear in everything. Okay, go ahead.
So n total is the number of atoms.
Total number of atoms. With these two, let's proceed. So last time I talked about another thing I want to recap is we talked about the potential energy curves. So we don't have to think about enthalpy curves. Enthalpy curves are harder to get. Potential energy curves are easier to get. And I think people in this department have stopped putting me on like candidacy exams or literature exams for like inorganic and organic chemistry students because they always seem to get so confused between internal energy, don't quote me on this, okay? Internal energy and enthalpy and free energy. Yeah, it's terrible. I mean, they use some quantum chemistry code which gives potential energy, and then they will go around claiming it's free energy, and it makes me scream, like real pain. It's terrible. Sometimes even their advisors are confused. That's another story. So we are thinking about the potential energy of two atoms. Let's say this is atom number 1. Let's say this is atom number 2, and we have a distance r between them, and we want to think about a potential energy curve. This potential energy curve looks something like this, and we have a depth that corresponds to the stability of that bond, right? And this thing will either be epsilon AA or epsilon AB or epsilon BB, depending on whichever bond you're looking at. We are always going to keep this as a negative number in the sense that if in isolation, all of you kind of like each other, you would like to hang out at a particular distance from each other, which is not always true. I mean, think about it. And no, actually, any two atoms will have something like this. They would like to come to a certain distance. Now, where it's that distance, that might change. But this is a very generic curve. A good example for this curve is something like A by R to the power 12 minus B by R to the power 6, which is known as a Lennard-Jones interaction. So this is an example. Next semester, we will, in 687, we will talk about curves like this more detail. So this is a curve, and we are going to work with these 3 parameters, okay? So with this, now let's think about what do we need? We need the mixing, the change in U before mixing and after mixing, okay? So we are interested in delta mixing U. And how do we define? Let me be careful with the sign. I think delta mixing U is U solution minus U unmixed. Okay, so let's start with U solution. U solution is going to be the number of AA bonds multiplied by the strength of an AA bond, and we are taking reference at when 2 atoms are infinitely separated, okay? Plus PAB epsilon AB plus PBB epsilon BB, okay? This is U solution. Let's call this equation number 1. Actually, let's call this equation number 2, because I want to use my assumption, this one, as equation number 1, where we wrote down the number of AB bonds in a random arrangement of atoms. Okay, this is U solution. Now, we talked about N total, right? Now let's split it a little bit. Let's say we have NA A atoms, NB B atoms, okay? And coordination number is Z. So And by what do I mean by coordination number? I mean something like if this is A, B, A, B, A, B, B, here the coordination number is 4, okay? Now I want you to think about what is Z multiplied by NA in terms of PAA and PAB. Let's consider a situation where there are no AA bonds in the system, okay? Think slowly and carefully with me. There are no AA bonds in the system. So it looks something like A, B, B, A, B, A, B, A. You see, any bond that you see is an AB bond. There is no AA bond, there is no BB bond. So I ask you to count the number of atoms A and multiply it with the number of bonds that atom A forms, okay? How should this be connected to PAA, PBB, or PAB? And I'm asking you for the case when there is no AA bond. That will come later. It's only AB bonds. Huh? Y plus 1. P is not. Why are you adding plus 1? PAB is not probability. It's number of bonds. We wrote this last time. Just to remind you, it's kind of misleading because I'm using P and P for probability. So a good point. P is number of AB bonds. It should be PAB.
Why are we assuming a lattice structure in this entire?
Just for drawing. Don't be upset, man.
No, I'm just saying that you.
It's just for drawing. Yeah, it's just for drawing. In real, so in a lattice structure, what is known as the G of R will be a delta function P. Okay. If you didn't have a lattice structure, it will be kind of diffuse. It's just for drawing. Purely. I'm not assuming lattice structure. I could move it a little bit. Yeah, go ahead, Sophia.
I'm still confused on how, like, what this equation means.
Alex.
Well, if we have only bonds between A and Z, so each atom A has Z bonds. So Z multiplied by number of atoms A is total number of bonds between A and B.
Yeah, so let's look at exactly. So let's look at it once again. Let's look at this picture. Let's forget about the edges. Let's look in the middle. So we have one AB bond, right? We have second AB bond, we have third AB bond, we have 4 AB bonds. So the numerator, the right-hand side is equal to 4 in this one, right? And we are going to ignore the edge atoms. The edge atoms are like the side dancers in a Bollywood dance or something, right? They don't really exist. They are only dancing in the background. You kind of ignore them. This is the B in the middle is the hero. Okay, so we have PAB is equal to 4. Is that clear? What is Z here? 4. Coordination number is 4. And what is the number of A atoms? If we are ignoring everything on the side, it's 1, right? So you can see why it makes sense. This is the easier part. This is only if there are AB bonds. Now, let's go to the other extreme. Actually, not let's go to the extreme. Let's just start adding AA bonds also, okay? And AA bonds and BB bonds, both of them exist now. So clearly, now I have to add something over here. It will not just be PAB because the number of bonds that A is forming is not just AB bonds, right? So I have to add something else. What should I add? It's actually 2PA. Yeah, this is very confusing. Those of you who are saying, okay, we'll go back home today and be like, oh no, that's not okay. Oh my God, what have I done? This is confusing. And again, the best way to understand it is if you have only A's in the system, okay? Forget about all B's. Now imagine a lattice where you have only A's. And then you can go and work through this. Okay? So I'm going to star this equation. It's a bit tricky. Even I get confused every once in a while. And in general, today's class, what I do want you to remember from today's class for exam is the expression for free energy of mixing for a regular solution, which I already wrote down, okay? Which is this delta H mixing is equal to this and delta S mixing is equal to this. That's what I want you to remember. One moment. If you get confused in the proof, don't stress too much over it. If you understand it, I will be very, very happy, but I'm not going to quiz you on it. Any questions?
This formula where N2 PA,
Hmm?
I don't see how it works like the same way we just did. We're not ignoring the entity, right?
No, we are not. We have to go and count everything. So, but all the idea here is that since we have to really account for contribution from both A's, that's it's fine. So you can't ignore the edges. You have to really take into account that the A bond is coming from. So this idea will work only if you start extending A in every direction and then think about it.
PAB are
Yeah, exactly. It's a large approximation. And it comes really because since we have to account for, it's double counting. Okay, that's what it is. So account for contributions from both A. Okay, so Z and A is equal to this much. In a similar way, Z and B is going to be PAB plus 2PBB. Equation 4. So now we can take 3 and 4 and put it in 2. Put 3 and 4 in 2. So what do we get? We get U solution is equal to epsilon AA multiplied by PAA, right? Epsilon AA multiplied by PAA, this term over here. But PAA can be taken from this equation 3 and written in terms of the other two things. So we are going to eliminate PAA, okay? So that's going to be ZNA minus PAB divided by 2. And I will write this equation again on the next page because it's important. Epsilon BB multiplied by ZNB minus PAB divided by 2 plus PAB multiplied by epsilon AB. So let's call this equation 5. I'm going to go to the next page and I will write this thing once again. So if you haven't copied, don't worry. So we just said that U solution is equal to epsilon AA by 2 multiplied by NaZ minus PAB plus epsilon BB by 2 NBZ minus PAB plus PAB epsilon AB. Okay, so this is my equation number 5. Let's do a bit of rearrangement. What does this become? If we rearrange it, what we are going to do is to take this term and take this term, which do not depend on PAB, and keep all the PAB terms on the right side. Okay, so this will become NaZ by 2 epsilon AA plus NBZ by 2 epsilon BB plus PAB epsilon AB minus epsilon AA plus epsilon BB by 2. Looks kind of complicated, but what is this physically? This is the internal energy without mixing. When you had A and B separate, you had AA bonds and the same double counting argument over here, which should now make more sense. You know, why did we do this? And you had, and again, before Vedant gets angry with me, it's not assuming a crystal lattice, it's just assuming an average some coordination number, okay? Because turns out liquids and gases are not entirely structureless. They still have some structure, right? If liquids are completely entirely structureless, then life would be kind of terrible, right? So they do have some structure on an average. Gases have lesser structure. So this is energy of pure A, while this is energy of pure B. Therefore, U unmixed is NA(Z) by 2 multiplied by epsilon AA plus NB(Z) by 2 epsilon BB. And this is what? This is our energy of mixing, right? We just wrote down. So if you look at equation 6, what did we do? We just left-hand side was here, the left-hand side was equation U solution. And we just said that all of this in this bracket, in this circle is U unmixed. So the difference is the free internal energy of mixing. Therefore, delta mixing U is equal to PAB epsilon AB minus epsilon AA plus epsilon BB divided by 2. That's equation number 7. This is already very interesting because we know that ideal gases won't have delta mixing U. But this kind of shows something peculiar. If you have two complicated elements, A and B, where the bond length of AB, the bond energy of AB was exactly the arithmetic mean of bond energy of AA and BB, it would again cancel out. You won't be able to tell. That's kind of crazy, isn't it? That, you know, these are not ideal gases. You have three things. Let's say this one is minus 14 electron volt. And let's say, I mean, what's an average there? Let's say that is minus 12 electron volt and minus 16 electron volt, right? Or whatever unit you want. I think this is an absurdly high number for an electron volt. Does anyone agree why? What is this in terms of KT at room temperature? Someone should know this. What is KT in electron volt at room temperature? No, 0.025. So this is like 560 KT. That's a very, very mega strong bond. You know, that's okay. But you can see so A and B have a bond strength of 14 electron volt, and AA has 12 and BB has 16. If you mix them, it will behave like an ideal mixture. That's very interesting, right? So you won't see anything. You will just get a perfect mixing, but it will be ideal, right? So this can lead to delta mixing U equal to 0, even for non-ideal behavior, which is kind of interesting. We are still left with PAB, and that's where we will use our, yeah, go ahead. Where would they come from? They just disappeared. If you look at equation 5, the Na and B term have all been absorbed into the energy of pure A and energy of pure B. They're gone. PAB itself depends on Na and NB, and that's what we are going to do now. We haven't, yeah. So let me write down these two equations, the two important equations now. So page number 5. So our two important, well, we have three important equations actually. Our three important equations now are delta mixing S is equal to plus R XA ln XA plus XB ln XB, right? Because we did not have to derive that. We just said, let's just assume the ideal behavior and let's just stick with it, right?
Should it be
Go
minus R? It's minus R.
Is it minus?
Yeah.
Yeah. So you have mastered your entropy now. Why did you think it should be minus?
The ln X.
There you go. It should be positive, right? So you immediately know. And yeah. Any questions? Okay, this is the first one. The second one is that delta mixing H is approximately delta mixing U. And that we just wrote down is PAB multiplied by epsilon AB minus epsilon AA plus epsilon BB by 2. And when you study all of this for your exam, let me be very clear and do something and mark it from here. Apart from here, not on exam, the next few pages. Okay, and soon we will get back into the exam territory and I will mark it again that we are back in exam territory. And we also had the equation for PAB. That was our assumption, right? And we had PAB was, what was that one? You remember it was linear in everything, right? So it was linear in coordination number. It was linear in total number of atoms. It was linear in XA. It was linear in XP, right? This was PAB. That's how we wrote it down. So now we can write down the full thing. With this, we can write down delta mixing G is equal to delta mixing H minus T delta mixing S. What is delta mixing H? Delta mixing H will be this term over here, where we are going to put the value of PAB in here, right? So that's going to be Z n total XA XB multiplied by epsilon AB minus epsilon AA plus epsilon BB by 2 plus RT XA ln XA plus XB ln XB. Okay. And we will now define our regular solution parameter, which we had earlier just thrown like that. Regular solution parameter is now defined as Z multiplied by N total multiplied by epsilon AB minus epsilon AA plus epsilon BB divided by 2. Everything from here, we are now back in exam territory. I won't say will be on exam, I'll say can be on exam, okay? So everything until up top of this derivation, I don't care about, but I care that you remember. And if you forget, this is not too, you can see why it makes intuitive sense, right? We derived it, all of this, but it is really telling you where is the, it's relative repulsion, right? That's one way of thinking about it. And with this, we can write down our free energy of mixing.
So now is the bond energy.
Bond energy.
So would that not, would temperature not affected?
No, potential energy is not affected by
What's
temperature.
potential?
That's the funny thing, right? That's why StatMech works, or thermodynamics works so nicely. They're really separate. It's beauty, right? U minus TS. Everything temperature dependent is in the entropy part. Potential, and this is why my inorganic chemist colleagues think they can do zero temperature DFT and talk about everything in the world.
But bond strength is right.
Bond strength is not temperature dependent. The potential energy curve is defined is independent of temperature. And there is a deeper reason for that. When we go to StatMech, we will see the Hamiltonian is separable and things like that. So potential energy curve is not dependent on bond strength. So potential energy is completely independent of temperature. So with this, let's write down the final expression. We have omega multiplied by XA multiplied by XB plus RT XA ln XA plus XB ln XB, where now I have given you a value for the regular solution parameter. It's the average coordination number multiplied by the total number of, actually, we will have a problem if we stay with the total number of atoms. Let's make it intensive, okay? Let's remove this and then talk about this in an intensive setting, right? Otherwise, we would have to write total NA over here also, right? Okay, let me do it in a way that does not confuse you later. Let's keep N total here. All we have to do is to multiply this also with N total. Therefore, per atom or in an intensive setup, delta mixing G. Should I do that? Sorry. Yeah, sorry if your notes are becoming too scratched up, but no, it's best to keep it this way. I think it will cause you more confusion. And let's just call this intensive. Sorry, I won't change it again. This is intensive, regular. Let's just call it intensive regular solution. I can hear Nathan scribbling very furiously. Intensive regular solution parameter. And this is plus RT. Okay, so everything is intensive. This equation is we derived it more or less rigorously, making some assumptions which you stated clearly, but it is quite powerful. And this will be really our foray into phase diagrams, more complicated phase diagrams, which we're going to do for the remaining part of the semester primarily. So let me write down this expression on the next page and then try to get intuition into it. Let's try to plot it for some competing values of omega and temperature. So this we are going to call equation number 8. Yeah, and there are theories of polymers, for example, like the Florey-Huggins theory, which people use to model all complicated things like RNA or whatever you want, which is nothing except this equation. That's it. This equation has been used for like so many things. Quantum dots you can describe using this equation, and you know how to correct it, right? So if you had some experiment and you wanted to go and correct this equation, let me first write it on next page, and then let's talk about how we might be able to correct it. So delta mixing J, G in regular solution model is omega XA XB plus RT XA ln XA plus XB ln XB. Let's say now you have a binary mixture and you try to fit the free energy of mixing using this, and you are not getting a good fit. What would you like to change in this equation? What could you change? Yeah, what could you change here?
And it's what I hear.
You would add a quadratic term, right? So you would start adding things like omega 1 XA square XB plus omega 2 XA XB square. All of those will affect the energy of mixing. There you know how to change it, right? And you can keep adding more and more. You can keep adding cubic term, and most likely you will fit things, right? I mean, if you are adding parameters, this is why neural networks are so powerful, right? They are so over parameterized, you will fit whatever you want. It's very hard to add corrections to the entropy term, right? It's not obvious how you would do that. And that is a really hard problem. So this would be easy corrections to delta mixing H. However, delta mixing S is harder to correct. And people have tried to think about it. There are many various approximations. We won't go into that. You know, it becomes very complicated. You have to not just think about pairs, you have to think about triangles and squares and overcount. It's a whole mess. The way to do that is known as cluster variation method, which was done by someone known as Kikuchi back in the 1950s. And that gets very, very messy. We won't be talking about any of that. However, we want to think about this expression and try to plot it. So, and what number did we give it? This is equation number 8. Let's visualize equation 8. So we know that the entropy part is always negative, right? So what we want to do is to plot this as a function of xb, okay? So we want to plot 3 terms. We want to plot delta mixing H, we want to plot delta mixing S, and we want to plot delta mixing G, all 3 things, okay, as a function of xb. And this is my 0 line over here. So if omega is less than 0, what's going to happen? How will delta mixing H look like? Delta mixing H is this part. Can it ever be positive if omega is negative? Because mole fraction are always positive, right? So you can do whatever you want. So if omega is less than 0, then at any T, at any temperature, low, high, does not matter, you will get let me use colors to make simplify things. So delta mixing H will look like a parabola. We know our delta mixing S is not like a parabola, but it kind of behaves the same way. It has slopes which are very sharp at both ends. And what's their net sum going to look like? An even deeper curve, right? Even more negative curve. So what happened here? What does this mean physically? Omega less than 0, and this is where having this equation that we derived for the value for omega is quite useful. So remember, omega is equal to Z multiplied by epsilon AB minus epsilon AA plus epsilon BB divided by 2, right? So if it was an ideal gas, things like to mix, right? A and B just hang out and you don't get just clusters of A or clusters of B, everything becomes clumpy. So if omega less than 0, what does it tell us about the potential energy of A and B? It tells us that epsilon AB is less than epsilon AA plus epsilon BB divided by 2. What does this tell us about the AB bond relative to AA bond and BB bond? Which is weaker? Someone said AB. This is more negative. Remember, we had defined these things to be negative. So epsilon AB being smaller actually means that it is going to be something like minus 100 kilojoule, while the average of AA and BB is a smaller negative number. Okay, you know what I mean. So this means AB bond is very strong. So just due to mixing by lifting internal constraints, you wanted A and B to hang out together. And on top of that, you're saying that A and B really like each other from a potential energy perspective, right? So it simply enforces that behavior. That's what's going on there.
That doesn't make, like, it's fine, the math works, I agree, but you wouldn't.
It makes 100% intuitive
No,
sense.
it makes, but where would you see this in, when you actually mix two liquids together? You don't, like, going back to the oil and water example, for instance, you don't see AB bonds being stronger, right?
There are, I can
Like
give
in
you
your
like
bond-
50 examples for this on Slack if you ask me later. It applies to lots of chemical problems.
That the
Yeah,
cross bond strength is
Yeah,
stronger than.
yeah. I am ready to bet at least 50.
I'm not going
I
to- I'm
think
not
I
going
have
to-
some examples somewhere over here. There are, and even like complicated electronic form behavior could be accounted through this. So yeah, there are a lot of settings where this could happen. Not all, okay, but there are a lot of settings where this could happen. And I can give you examples if you remind me. You just go and find it, you will find it online. But if not, ask me. Yeah, go ahead, Patrick.
Does it have to do with like different electronegativity?
Yeah, that's why I said it will in the end up it will end up becoming how the electronic clouds are talking to each other, right? That's the whole idea. So in class, so the reason why you're thinking this is because you're thinking about a classical picture. But in quantum land, all sorts of things can happen. Okay, and we are basically getting ready to describe the whole picture, right? So this is one picture. Omega less than 0. At any temperature, we will have this behavior. It does not matter, right? You will always like to mix. Now, let's think about omega positive, and we will look at high temperature and low temperature, and then we will stop for today, and then we will come back after Thanksgiving break. So omega less than 0, any temperature, you will just get mixing. Doesn't matter. A likes B more than A likes A and more than B likes B. He's on it, he's finding it on the internet. If omega more than 0, then we have to think about two different regimes. So let me remind, what is the expression? We have delta mixing G is equal to omega XA XB plus RT XA ln XA plus XB ln XB. So I don't want a parabola, sorry. So we have something like this, where this is XB, starts from 0, goes to 1. And this is my line for 0. So once again, I should have labeled things here. So this is delta mixing H. This is delta mixing S. And this is delta mixing G. So omega positive, is it going to affect delta mixing S in any way? No, right? That stays the same. So that thing is going to be just like you had before, something that goes up to 0 at both ends with a very sharp slope. Now delta mixing H is going to be positive. So this thing will be a parabola, but which is upwards. I was using color red. So this is going to be something which is upwards. Okay. Now, if the temperature was, and let me draw one more thing and then we can really look at it together. Again, 0, xp1. And now I'm going to draw a delta. No, let's just do this. So this is delta mixing H. And oh, I see what was confusing me. So I'm not plotting just delta mixing S, I'm plotting T delta mixing S, okay, just to keep things consistent. So this over here is that correct? Did I plot T delta mixing S? Nathan, you are the guru of this one.
Yeah, because you have this, that would be RT.
Delta mixing S is positive, right? So this must be minus T delta mixing S. That's what I plotted. So this is minus T delta mixing S. And over here, I'm also plotting minus T delta mixing S. And the same, and I will tell you what's different between both of these. So which one is at a higher temperature, left or right?
So I have a cool
Go
question.
ahead.
So for delta mixing H, based on the equation we gave here,
Mhm.
it's not a function of temperature.
No, that's why in both plots, that did not change.
Okay.
Exactly. That is not a, and that is something you should always remember. And there is an approximation here. Enthalpy does depend on temperature. Potential energy difference is what does not depend on temperature, right? This is why quantum mechanical calculations can be done and you can get away with it, you know. Enthalpy does depend on temperature, but here we assume that the enthalpy change is the same as potential energy change, right? We made that big assumption. That's why we are working with it. Vedant is really unhappy. I'm sorry, Vedant. Yeah, go ahead, Sophia.
What is the difference between these two?
Oh, that's what I'm asking you. What's the difference between left and right? So one of them is a lower temperature, one of them is a higher temperature. So my question for you is which one is lower, which one is higher?
Left, higher. Left.
Which is lower temperature?
Right.
Good. Is everyone happy with that? This is low T, this is high T. And notice that the delta mixing H should be the same height. That's not going to change. The T minus T delta mixing S became deeper or higher. So if the temperature is so high that this one minus T delta mixing S is really deep, will adding a little tiny bit of delta mixing H have an impact on it? Probably not, right? So if the temperature is high enough T, if we have a high enough temperature, this term will dominate. This will dominate. So the net effect on the delta mixing G is going to look like this. So you won't be able to tell what went on. It will look similar to what you had in the previous case. The right one is the most interesting. And this is when the enthalpy and entropy are starting to fight each other, right? So why are they starting to fight each other? Omega more than 0, what does that mean? Omega more than 0 means that epsilon AB is more than epsilon AA plus epsilon BB by 2. So this tells me that, let's say all the A are the chemistry students and all the B are the biophysics students, right? So the chemistry, I would like all of you to mix together. but the chemistry students really do not like the biophysics students, right? So there is a competition. If the temperature is high enough, the mixing will dominate. And the fact that you don't like each other, no one cares. You're purely mixed, right? If I was just like kicking you randomly in every way, you will be mixed. There is no other way. But if the temperature is not so high and the entropy is not that dominant, then there will be a competition. Okay, so the entropy wants A and B to mix, but the bond strength says A actually likes to hang with A, B actually likes to hang with B, A does not like to hang out with B. And you will get a competition. And the net effect starts to look quite beautiful. You get a curve which can start to look at the very, and this is something which I personally find very beautiful. At both ends, at xp is equal to 0, which one is going to dominate? Delta mixing H or delta mixing S? Why? It has the power of L'Hopital. That's the power of El Hospital, right? It drops down with a slope of -infinity, right? So delta mixing S drops down with a slope of -infinity, and delta mixing H goes up with a puny little quadratic. And the -infinity is going to beat the hell out of quadratic, right? So at both ends, you're always going to get delta mixing, and I'm going to zoom in on this. At both ends, the delta mixing G is always going to drop down. This is super powerful because now we are talking about regular solutions where there is interaction energy. You can go and look at most complicated materials. The free energy of mixing actually does behave this way. It goes down. But in the middle, all sorts of things can happen. It will go up and have a little hump and come back and go down here. And it depends on the competition between omega and T. And this is what is our first example of phase separation. You are going to separate into two clusters. You will have a A-rich cluster with some B and a B-rich cluster with some A. And you can see why this competition happens, right? Because the entropy and energy are just like so confused. When we come back, we will talk about what is the composition of these clusters, how exactly do they happen, can we calculate? We will talk about something like Lever rule, which will allow us to calculate how much of the clusters form. But this is, for this regular solution model, that's why I find it to be quite beautiful, because with such simple algebra, you can start to see very complicated behavior. This is where we are going to stop today. It's a lot of new material, complicated material, relatively. Any questions? So just to remind you, the part from here, not on exam, all the way till page 5 can be on exam. That part is not on the exam, but I do want you to remember the expression for omega, because you can see why it is important, right? I just threw out a regular solution parameter. It does not make any sense. But if you know it is a difference of two bond strengths, and Vedant has a homework, he's going to go home and find out why he thinks that this part is total crap.
No, it's fine. I didn't realize that omega is less than 0. If
Yeah.
the sign changes, it just means
Yeah.
that it's ordering more.
Exactly. There's lots and lots of examples. And like I said, this model can be applied to complicated polymers, DNA, RNA, quantum dot, nanomaterials, whatever you find. And we have ways of making it more complicated by adding terms to XA, XB, right? The entropy is really hard. So when I was an undergrad, my first paper was related to this clusterization metric by Kikuchi. And that was like one of the most terrible summers I have spent. It was just like crazy. So I have like painful memories. The entropy, and I can send you the paper if you want. You can also have painful memories. But we won't talk about that. We will stick with the entropy like this. And another thing that we did today was to remind you of the definition of entropy. It's not disorder, it's not order. It's Nick staring at you from 500 feet above and telling you, think about internal constraints, okay? That's what is maximized, which connects to order and disorder. This is something which is, really the heart of Chem 684, this formula, S of NEX more than equal to S of NEX with internal constraints. Just remember this one, don't forget this. Okay, so see you next Tuesday. I hope all of you eat a lot of food and like go totally comatose after eating too much food.